So in this video, we'll be looking at what happens when you bring two atoms close together. So basically, we'll be looking at the energy profiles. We'll actually get started with what is a potential well. And once we understand what is a potential well, we'll actually look at why the profile of potential well the way it is. And for that, we'll have to revisit few basic concepts in physics, that is the Coulomb's law and the electrostatic potential energy. So once we understand that, then we will look at the periodic potential well. So basically what happens when you have many such potential wells actually coming close together. So once we look at that, this will eventually lead to the splitting of atomic orbitals. So once we understand the splitting of atomic orbitals, it eventually leads to the formation of energy bands. At the end, we'll actually take an example and we'll look at the energy band diagram that is commonly found in device physics textbooks and try to understand the diagram based on the concept that we will be looking at. So let's get started. So let's start things simple. So let's look at a reference potential energy and see how the profile of this energy level changes as we have an atom close to it. So suppose the reference potential energy looks something like this, like a straight line. And now we have an atom that comes close to this reference energy. So now the question is, what happens to this energy profile? So if we actually look at the energy profile, it looks something like this. There's a dip in this potential energy level. So that's why this dip is commonly called as a potential well. But now the question is, what is the reason that the potential well is dipping in this fashion? So to understand this, we have to go back to high school physics. So let's start with Coulomb's law. So we know that Coulomb's law states that force is equal to kq1 q2 by r square. So now what I want to actually emphasize is on, so how does the plot actually look like between force and the distance? So we have on x-axis the distance and on the y-axis we have the force. Let's say on origin we have an atom. So let's say I bring an atom from infinity close to this atom. So if we actually try to plot how the force looks like, the plot looks something like this. So as we get closer, the force keeps on increasing. But force is not what we are actually looking for. We are actually looking for what is the energy. If we actually look at this graph and ask a simple question, what is the energy required to actually move the atom from position R2 to R1? Then the answer is actually straightforward. It is just the area under this curve. Suppose now the question is, what is the energy that is required to move an atom from infinity to point R2? Then the answer is simple. It is just the area under this graph. So now let's try to mathematically understand how this is actually coming. So we know that energy is actually given by the integral of force dot dr. So if we actually do the integration of this relationship, so we'll end up with energy actually having an inverse relationship with the distance. So this is actually called as a hyperbolic relation. Now let's actually do the plot of energy versus distance and see how the plot looks like. So now on the x-axis we have the distance and on the y-axis we have the energy. So if I have an atom that is brought from infinity close to this atom, then we'll see the energy profile look something like this. Similarly, if I have an atom that is brought from the left, and if you actually look at the energy, the profile looks something like this. So commonly what people do is they actually approximate this energy profile to look something like this. So the same thing is done on the left hand side as well. So if you look at it, this is looking exactly like the potential well that we had. And we understand that this is an approximation. But the actual profile looks something like this. So this approximation is commonly done to actually reduce the mathematical calculations when you are trying to solve the Schrodinger's equation. So this is what happens to your energy profile when you have a single atom. So what happens when you have multiple atoms? So let's take an example of a silicon crystal, and we know that in silicon approximately we have 10 power 22 atoms per centimeter cube. And a crystalline silicon, the atoms are periodic. So in simple terms, what it means is the atomic distance between the atoms of silicon in all the directions are same. So that is in x, y, and of course even in the z direction, that is out of the plane and into the plane. So it is all the same. Suppose we have two silicon atoms, and let's see how are the energy profiles affected when you start bringing those atoms close together. So the first atom, the profile looks something like this, and the second atom, the profile looks something like this. Let's assume that it has 2 electrons filled in these orbitals. One more thing is the atoms are actually a bit far away from each other. They are still not very close. So by looking at this energy levels, there are few observations that we can make. And also, let's say we have this empty orbital as well for these two atoms. So the first observation is, for the electron to move from this atom to this atom, it cannot actually directly tunnel through this energy barrier. So basically there is this energy barrier that this electron has to overcome in order to move to the other atom. So the path for the electron to take would be something like this. It has to first cross this energy barrier, then it has to move into this empty orbital. So now let's try to bring these atoms close, and let's actually specifically look at what is happening to this barrier. So now when we bring the atoms close together, we can see that the barrier initially was this height. This was the initial energy barrier that the electron had to cross in order to move to the next atom. Now the barrier has reduced to this one. So we can see that this much of energy barrier has actually reduced. So as you keep bringing the atom close together, actually this barrier keeps on reducing. Eventually what will happen is you'll end up in situation that looks like this. So now here is the problem. We know that according to Pauli's rule, you can't have more than 2 electrons in an orbital. But now we have 1 orbital and we have 4 electrons. So this is a problem because it is just violating the Pauli's exclusion rule that we know. Of course, we can ask this question, where is this Pauli's rule actually coming from? It just comes out as a mathematical result. And of course, the math is not simple. So to just keep things simple, we can just think that electrons obey Pauli's rule. So now this is a problem. So now what happens when you bring atoms this close? So the answer to that is the orbitals actually split. And this is something you would have actually commonly seen in your high school chemistry when you actually learn the molecular orbital theory. So you would have seen something like this. You have electrons in this fashion in these orbitals. So when you bring them closer, now the orbitals split, and the higher energy orbital is called as the antibonding orbital, and the lower energy level orbital is called as the bonding orbital. Electrons first occupy the lower energy levels and then they occupy the higher energy levels. Suppose you had 1 electron here instead of 2. The electrons first, it would occupy this. Once this is filled, then it will go and occupy the antibonding orbital. So to give an analogy of how this bonding and antibonding orbitals are formed, so you can think of it as there are 2 waves that are actually coming in the opposite directions. So you have 1 wave and so you have 1 more wave, and they are actually coming in opposite directions and they will collide. So now the question is, what will happen to the resultant wave? So we know that there are 2 possibilities. So we know that either there can be a constructive interference where the energy of the wave has increased, or else there can be a destructive interference where the energy of the wave is reduced. So the common terminology that we actually see in solid state physics or device physics textbooks are that, when you have this bunch of antibonding orbitals, they actually form the conduction band. So when you have a bunch of bonding orbitals, it actually gives rise to the valence band. So this is how the conduction and valence band are actually formed in a solid. So actually let's look at this splitting of orbitals in a little more detail. So in this plot, I'm actually plotting the energy versus distance, but now the energy is on y-axis and the distance is on the x-axis. So I'm actually looking at the energies of the orbital. So far as we have seen, when you start bringing the atoms close together, the orbitals are not splitting, it is the same. Once you bring it further closer, what happens is it starts splitting. So the higher energy orbital is the antibonding, as we saw, and the lower energy orbital is called the bonding orbital. So by looking at this diagram, we actually see a problem. The problem is the bond distance, that is the distance between 2 atoms when it actually forms a bond. So according to the graph, it is 0. What exactly I mean is, we know that the covalent bond, when it forms, the total energy of the system is actually less, right? So from this graph, it looks like the total energy actually comes at this point. So basically the distance is actually 0. So in short, what it is trying to tell us, the systems or the atom is actually having minimum energy when the atoms are actually touching each other. And we know for a fact that this is not true. And the reason that it is not true is, so far we have only considered the force of attraction between 2 atoms. But when you actually try to bring the atoms very close, there is also this force of repulsion between 2 atoms. So if you actually look at the way the orbitals split, so you will have the antibonding orbital that splits. Similarly, the bonding orbitals also split, but after a certain distance, what happens is the energy of the bonding orbital starts increasing, and this happens because of the repulsion between 2 atoms. So now it is very clear. If we actually look at this plot and see what is the bond distance, that is the distance between 2 atoms, it looks like the bond distance is somewhere here. So let's call this R1. So there is one more thing that you can actually understand by looking at this diagram. The slope of this bonding orbital is actually different on the left hand side and on the right hand side. So if you actually increase the temperature of this crystal, crystal, what happens is the atom actually moves towards the right because the slope is actually lower. So we can conclude that as the temperature increases, the bond length actually increases for such crystals. You could also have a case where the slope on the left hand side is actually lower compared to the slope on the right hand side. And in such cases, when you increase the temperature, actually the bond length actually reduces. So this is also additional information that you can actually get by looking at this diagram. So finally, to end this discussion, let's actually take an example and make sure we understand all the concepts that we have looked at so far. So let's take an example of silicon. This is the diagram that we have commonly seen in device physics textbooks. So we know that the atomic number of silicon is 14. So if you try to write out the electronic configuration of silicon, it comes out to be 1s2, 2s2, 2p6, 3s2 and 3p2. So in this example, we are considering the total number of silicon atoms as n. So this is the total number of silicon atoms. So we can see that when the atomic distance is very far, at 3s orbitals, you have total 2n states, because we know that in s orbitals, the total number of states is 2. And there are 2n number of electrons. So that is, we already have 2 electrons that is filled. And in 3p orbital, we know that in p orbital, the total number of states is 6. So since we have n number of atoms, the total states is 6n. And since we have 2 electrons, the total number of electrons in this orbital is 2n electrons. So we can see that as we are actually reducing the atomic distance, we can see that the orbital is actually splitting into 2 energy levels. But there is one interesting thing that we also see here. At this point, the energy is actually also merging, and again it is splitting. So what exactly is happening here? So the answer to that is the orbitals are actually getting hybridized. So we would have heard of hybridization, and it hybridizes into sp3 orbitals. So the orbitals actually mix, they form sp3 orbitals, and they again split as you try to reduce the atomic distance. So we can see that once the energy levels are split, so you have total of 4n states as higher energy level, and we have 4n states as lower energy level. As we know that in sp3 we have a total of 8 states, right? Because p had 6 and s had 2. So once it mixes, the total number of states is 8. And it actually equally splits into 4 states. 4 states in the antibonding orbital and 4 states in the bonding orbital. And we know that electrons actually start filling from the lower energy orbitals. And that's what is actually even mentioned here. There are 4 electrons that is actually filled in the lower orbital. And we can see that there are no electrons in the higher orbital. And also we can see that this is the atomic distance, because this is where the total energy is becoming minimum. And you can see that the distance between the top of the valence band and the bottom of the conduction band is what is giving the band gap. So this is what actually happens when you try to bring two atoms close, and this is what happens to the energy profile. So this is what is actually called as the band theory of solids. And the reason why this theory is so important is, so first thing is it tells us how these energy band diagrams are actually coming, and next thing is based on these energy band diagrams, it helps us to classify the materials as conductors, insulators or semiconductors. So that's the end of this video, and thanks for watching, and see you in the next one.